my name is Uwe Hilpert. I am from Wenzel. So this is a joint contribution of, well, I would say part of our common work, one could say so. And need some adjustment. And so first, let's have a quick look of our companies. So as I said, I am from Wenzel. We are a metrology company. That means we measure object things. We were founded in 1968, and we are in Germany in the field of the metrology, the largest family-driven company, meanwhile in the second generation. So our sales volume is round about 87 millions with 650 employees worldwide on 17 locations. Our sales, and we have over 50 sales and service partners with 5 product lines. So our core product line is a classical tactile CMM, as well as optical high-speed scanners. And today I will present you about our CT product line. And sold machines, about over 10,000 machines on the market. Our volume is, in terms of sales volume, 11% of R&D. So it's a fairly good amount. And our machine life, service life on all our machines is over 20 years in operation. So as it concerns to Renishaw,
I will take over from
I would hand over to Sarah, please.
So in sort of light of comparing the length of sticks, Renishaw is equally as old as Wenzel. I think we came into light a few years after. The two companies have held hands, essentially, one not surviving without the other, with the invention of the touch trigger probe, which most of Renishaw has been built upon since the 1970s. We actually now have quite a large cohort of employees of nearly 5,000 now. And we break into a little bit more than the CMM world these days, including encoders, medical products and devices, additive manufacturing, and obviously we now make a CMM as well as the touch trigger probe. We do spend a little bit more on our R&D, which is one of the departments that I work within. I work as a global entity to Renishaw, so I deal with everything from all 37 of our subsidiaries and countries that we work within. So I kind of get to touch everything that Renishaw has sort of been involved in and all of the product lines that we deal with. I will talk on behalf of our additive manufacturing division today. So any questions, take with a bit of pinch of salt, because I see much more of the product development and process development side of our additive manufacturing, not necessarily our machine manufacture. But I think Uwe is going to start off the presentation today with a little bit of an introduction as to how these two worlds live in synergy with one another, and going forth in the aerospace industry, CT and additive manufacturing will have a wonderful partnership, hopefully with a little bit of detail from us today. So you get to introduce us now.
Yes, thank you. So this is an outline of our presentation. As Sarah mentioned, it's twofold. So I will start with the CT topic. I will give a brief overview about the principle of computed tomography, which consists out of the influence of the materials density, with, in my opinion, is the most dominating influence on the CT scan. So then, as we have to cover different topics, I need to talk about how surfaces are extracted out of the CT data. Well, CT data you may know from the doctor, from the hospital. We talk about some images, but we want to measure on them. So I have to cover this topic. On the other hand, another application we will see today There is something about defects, so we need to talk about smallest feature size we can detect. Then comes to prove what their methods exist, how to prove accuracy of CT results. And then I start with a very small example of applications. And then comes the right-hand side. Then Sarah will cover the side of the additive manufacturing with those different points here. So let's start with the principle of the CT. So for those of us who just does not exactly know how this works, maybe at least in medicine. So we talk about industrial CT, which is different from the medicine CT. So the most difference of industrial CT is the object spins around. We need to turn an object, and this is most easy. In medicine, a human or whatever, a patient cannot turn around 360 degrees. So the complete machines turn around the patient. So in industry, this allows us to implement a most compact design when we rotate the object and not the apparatus around. So this is one thing. And here we can see on the left-hand side, well, we need an X-ray tube that emits X-ray light. Then the object can be not only rotated, but also moved in between the X-ray tube. And on the right-hand side is the detector, which collects the X-ray images. I would compare it like in the good old days at black and white negative images, because that's not all. What comes out in the end of a scan is a so-called image stack. And this is calculated by computers. And then computer calculate from the 2D negative images a 3D positive image. So and this image is saved to disk as block. And as in 2D, one would say the images consist out of smallest elements, which we call pixel. In 3D, we have these elements are called voxels because of volumetric pixels. So this is an artificial word here. And that's then the result. And one can imagine that in each, so the object is cut into very tiny cubes during the scan. And in each voxel, in each element, there is a material information among the density. So this comes out of a CT scan. This means our first application when we make images. So on the right-hand side, on the left-hand side, starting from the left-hand side, I can display an image from such a CT scan here in any arbitrary slice, and one sees that we have a black and white, a positive image. That means the darkest color, black, in this case, is the material with the lowest density. In most cases, this is the air which surrounds the object. And then, independence of the object density, the gray values are higher. So this means that the highest gray value codes the highest density in such a voxel. And this can be displayed as image. So this is a very classical application in terms of non-destructive testing. Well, I said density. One can imagine that there is almost an infinite amount of materials combination that we can scan. So, well, I break it down to that periodic table of the elements. And when I code the compatibility of the element, of a specific element with X-rays, this means which easy it is for the X-rays to penetrate an object with this made out of this material, then it shows up that on the upper left corner, we have the hydrogen, which is the lightest element, and so it applies the least resistance to the X-ray. And on the down right corner, we have the elements in the last row. At least one knows the lead. So the lead is the material we in fact do not really want to scan, but it's a very, very important element because we're dealing with X-ray, so we need an X-ray shielding, and this is made out of lead. But as element to be scanned, we don't like it really, because it would imply to apply a very, very large energy to scan only very tiny objects made out of lead. So this is an overview, and one has to keep that in mind when we're dealing about X-rays and especially tomography. So, well, I talked about that one application is a metrology application. And a metrology application means we have to measure. And the measure output is output of millimeters. Let's say a diameter, the diameter of a cylinder. But in the first run, on the upper left corner, this is an image. And the question is now, well, if black is the air and white is the material, what is the diameter of this cylinder? Then it comes to image processing, because we want to be accurate. So, and there is a way how to process such an image. When we display a histogram out of our volume data, then we see on the left-hand side, we have a very high material peak, which corresponds to the material with the lowest density on the left-hand side, but the highest volume. This is the air around it. Then comes a very broad valley. And on the right-hand side, there is a material with higher density on a 16-bit scale and lower volume. And this is the material of the object. So, and in finding the correct diameter, we need to apply a threshold value in the middle of this to separate those materials. And with some pre-processing calculation, we can display points and triangulate them and export those triangulated surface as a so-called STL data, stereolithography file format, to disk. So this is the main process that is built upon image processing. So we have two applications. We have the application of just making images and displaying defects, and we have the application of metrology. Talking about accuracy, one word more talking about accuracy, because if you may notice that when it comes to the diameter, the way of the image processing implies that the diameter in the most cases is more precise than the size of a voxel. So please keep that in mind, that if we talk about precision, accuracy, precision, then our result in terms of diameter, wall thickness, whatever, measurement, millimeter, the accuracy is more precise than the pixel size, voxel size in 3D. The problem arises how to prove it. One step before I talk about the proof, there is another thing. As it comes to the image processing, I have to talk about resolution. So we strongly separate the accuracy in terms of a metrology result and the resolution of a scan. Because the resolution is different, this has to do something with the size of a voxel. So on the left-hand side, let's imagine we have a very tiny object on a piece of paper, on the table, on a piece of square paper. And our object is smaller than the grid. So our CT scan result will smear out the object and the size and the shape among several of those of voxels. And also, in addition, the material density value is not preserved. So only if our object is getting larger or the resolution as ratio to the object size is getting smaller, around about 5:1, then we can say in the image, well, yes, we have enough information to extract a point cloud that describes the diameter and the shape of the object. If this value is not preserved, then we can say yes in a way of non-destructive testing. Yes, in the image data, we can see there is an inclusion or a shrink hole or whatever, but no, we cannot export or generate a surface for that particular feature. So we only talk about accuracy if this ratio is preserved or larger. Okay, now talking about a proof of the accuracy. So the proof of the accuracy is a method we use such, we call this, you may know this from a tactile CMM. This is tips, stylus tips made out of carbon rods with ruby spheres on it. And this artifact is tactilely calibrated. So as we are accredited for this process, so very few companies in Germany and worldwide are accredited to do this. So we have a very accurate reference values for each center point of each sphere. And in addition, we can say not only this is the value for the center, we can say in addition, this is the uncertainty for the value of the center because we have a tactile calibration. And this is the most important thing for a calibration, is not only giving a reference value, so it's the main point of a calibration means giving a reference value and in addition an uncertainty for that reference value. Okay, and the next step is we scan it in the CT. And then we can display in the end on the right-hand side a graph that displays over the lengths just the difference between our well-known accurate value of the tactile CMN and the difference of a CT. So this is a way how to prove the dimensional accuracy of a CT. Okay, a very small application example because of Sarah will show us more about this. So when it comes to additive manufacturing, we have, as I explained, we have a possibly application of non-destructive testing and of metrology. Let's scan an additive manufactured part. As it comes out directly of a SLM machine, and it still has structures on it to stabilize it during the process, during the manufacturing process. And then the structures are removed and the part is treated in whatever way. And then the question is, well, does the part fit in the end where it is supposed to be implemented? And there CT can help in different way, scanning the part in the complete process after removing of the structures, before the hot pressuring process, and comparing every result with the nominal value, with the CAD value, and displaying this in a nominal actual comparison so that it's color coded. And green means that the part is still in tolerance. Red means that the part there's too much material, could be removed. And blue means, well, there was a removement, but it was too much removement, but we cannot glue material anymore on the part. So in this way, CT can help in the complete process of the additive manufacturing with in the design process as well as in the production process. So, well, only one slide about machines. So talking about machine, this is a short overview about the machines. On the left-hand side, we talk about CT scanner in the size of a tabletop system, will fit on any table, well optimized for smaller parts. Then we have some mid-sized class which exhibit high power and low footprint. Then on the large side, we have a machine which is most cost effective, made for heavy duty, and it's fast. And on the right-hand side, we have the universal class. Well, it's our flagship at this point. It's the highest flexibility, which means the largest part volume, the highest resolution. Yeah, then it depends on the application, which system would fit the need. So at this point, talking about machine, I would now hand out the control to Sarah. Please
we
talk
did
us.
joke earlier that we were going to play catch with the controller, but we've decided not to do that. I'll start off in a very boring manner of going through our additive machines. We have primarily 2 machines at the moment in the business available to customers. The Q, which stands for quad, which is a quad laser system, basically designed to be incredibly fast. Rather than building with a single laser, you can build 4 times as quickly with 4 lasers. And then obviously the S over there means single laser system. It's exactly the same as the quad, the way that it's built for single material use, and its hopper system and everything is exactly the same. We just have one with 4 lasers and one with 1 laser. Not to bore people with that, because again, I'm not a salesperson. I'm the person who sits here and sort of works on process development and what additive can do for you guys. It's a buzzword at the moment. I think if I asked the room, have you heard of additive manufacturing? You'd probably all put your hands up. Renishaw works in the business of metal additive manufacturing, which I think is quite an important one. I had a meeting the other week and someone thought we did plastic, and I was like, I'm sorry to disappoint you, we don't. But I think the utilization of additive manufacturing is now becoming quite more in synergy with the rest of industry. Now that our capabilities are a lot better, we've moved, I think I'll talk about in a little bit, from sintering. I think the customer profile on that was we used to make really porous things and additive used to be a bit rubbish, but we've now moved into sort of laser melting, which means we have fully consolidated parts, and their sort of freedom of design and freedom of dimension allows us to add additive manufacturing to lots of different parts of industry, be that from sort of prototyping, you only want to make one thing of something, all the way through to sort of, doing direct replacements. I want to make this in a better way. We only make 10 of them a year. Additive might be a little bit more suitable for that. One of the cool things that comes into additive, and I guess it's down to a person's ability to design and their imagination. I got one of the best questions, I think, in the 3rd week I work at Renishaw is, oh, we've got a free slot on one of the machines. What do you want to build? My brain just exploded completely, and I ended up making Pokemon because I'm apparently ridiculously sort of single-minded in that sense, but it's not designed for additive. When you get into the realm of actually designing for additive, the shapes, the possibilities, the things that you can make become very, very interesting and intricate. From sort of heat exchangers where you can have structures that you cannot make in other systems of manufacturing, you can do with AM. And when you design specifically for AM, that's where the magic really, really happens. With that new idea and that new exploration into sort of a reasonably new manufacturing process, especially in the world of aerospace, validation becomes quite tricky. We're taking something that everybody knows and we're changing it. So I think it's worth pointing out now, everybody thinks that AM is going to take over the world. It's most definitely not. We like to think of it very much more in reality. It's just another part of a skill set. And I think we turn away more people who are like, oh, I want to make this with additive. And we're like, nope, go away and do subtractive. There's absolutely no point. But it does sit within a really nice tool set for an engineer and manufacturers that AM has got its place. One of the issues we have, I'll come on to in a minute, but I forgot, we need to define what it is. Again, I've said we do metal additive, and that is the sort of process of making a part in an additive fashion, layer by layer. I've given a lecture on this, and I apologize for the patheticness of my ability to make flow diagrams and stuff like that. But essentially, we use laser powder bed fusion systems. So we have a big old bucket of powder, sits on a bed, run a laser over the top of that, melt the material, place another layer of powder over the top, melt that material, and it kind of gets built up. And I like to describe it sort of as when you're making a wet sandcastle. You build that up layer by layer, and then essentially you break that out from the powder afterwards, and you've got yourself a nice solid part. I have to give you a little bit of notice. I made these intentionally terrible. This is not what additive actually looks like, but for the sake of the presentation, having things really, really porous and other issues that happen with stress cracking if you haven't built your part perfectly for additive manufacturing because it is a skill to do so. You've put your supports in the wrong place, you haven't done your underpinning, you've got really tight angles, you're working against gravity. We can have all sorts of things that happen. Too much energy density into the part, you can get sort of big old holes like pulling in as you sort of boil your metal, as you're trying to melt it, you overmelt and you get all sorts of horrible things going on. Uwe earlier was chatting, dimensional metrology, that outside of that shape, the things that you can't touch, maybe with an additive part, especially when you've got internal channels and you need to measure where those are they where the drawing has said they are, and all these kinds of things. There's a secondary layer to that, which I think comes into, how much do we trust AM? And CT is an incredibly important tool to us now in doing that type of validation. I won't bore you with this because Uwe already explained it, but here's an AM part. I've used a very known shape. It's just one of our density cubes that we use for doing process development. And essentially the CT that we use with Wenzel allows us to sort of search around in our material. Again, sorry, this isn't real. I've done this on purpose. One of the things we do, and we do for a lot of aerospace companies, is we do need to validate our parts. There's a certain allowance of porosity that is acceptable. And I think for the sake of fatigue life and some of the roughened surfaces that we have in AM, unfortunately, the border parameters and the border area, which you see here in green, is a really vital component in how we sort of trust our AM. And we usually do this destructively. We go through hundreds and hundreds and thousands of test pieces. When we change our material, we change a process, we're trying to design very specifically for a customer. We have to think of these things and how the material behaves. But that is really time consuming and quite terrible. We've now moved into sort of doing these in a non-destructive way, because if this wasn't a cube and this was a full part and we have risky areas of overhangs and complex geometries, we need to know that that part is safe to go into production and safe to be used in, say, aircraft, for example. It's a really big thing. But I think one of the challenges that we have now is we've managed to do metrology of measurement. We can do skins, we can do the outsides of shapes. There is a distinctive sort of lack of validation in measuring and validating internal structures and porosity and fatigue, like initiators and all those kinds of things. And I think we get asked this a lot. We get fatigue properties, something you have a 50 micron pore size is acceptable. Anything above that is an absolute no-no within 5 millimeters of the sort of edge of the structure. And unfortunately, when you're doing CT, you have to bear in mind you're doing an awful lot of work blind. And there's a lot of software involved, which as soon as you take your CT scan and you reconstruct it, you've already changed what was real into something that's not real. And all of that processing from smoothing data, reducing your signal to noise, you are artificially changing everything. So your certainty and your insurance policy of what is inside of it is decreasing every single time you manipulate that data. And one of the worst cases of this is, someone's asked me, what filter have you put on? What threshold are you using? Uwe showed a wonderful image earlier explaining how it's difficult to measure from a single spot, because that edge region, when does it start? Where does it stop? When you can't form a surface around it because it's so small. And this is something I pose to the room as we need to find a solution for it. I know there is conversations out there at the moment of standards and standardized testing for this. But another scenario on this, not only are you changing what you're building with every parameter, every percentage change on your laser power, every pathway, every pattern, every STL scan you have, every single CT scanner is also different. Different detectors, different setups, different everything. So it's really hard to compare apples to apples. There is a lot of work being done, I think, across the UK at the moment, which is where it's quite fun to work with Germany, because it's over the pond, it's a bit different. And the way that we're dealing with these problems is all very subtly different. But I just wanted to leave you with this kind of idea of definitions and how definitions in this industry are very, very important. We talk about dimensional metrology. We're in sort of the business of it with all our encoders and our CMM products. And we can measure dimensions very, very well. I've coined the phrase internal metrology. Sorry if anyone's toes have been stepped on, because I not sure what we're exactly going to call it, but we need to find a way to measure internal features to allow for that sort of growth of AM into risky areas of manufacture and industry, especially in aerospace where human lives are at stake. How are we going to start deciding what's acceptable? I know there's loads of standards out there for porosity sizes, but when it's so difficult to measure with a level of certainty, it just is a question for the room, I suppose. I'm actually now going to hand back to Uwe, because the way that CT and AM actually now work together with being able to
Thank you,
build, think and build, I will hand back.
So this is a draft of a process that's already implemented at some customer, partly. So we have loops, process loops that can run independently or independence of. So starting from the left-hand side, there is a question, just ask a part to be manufactured, as we heard. So the first question would then be, well, do we have a digital model or not? But we have the part, this would be sufficient. So in this case, we would directly go to a process called reverse engineering. So it's just, in this case, converted it from a cut to a STL model. This is done in second way. So if we have a cut, we can directly convert it and put it in the scanner. And if we don't have a cut and only have the part, it would be just then put it in the CT and generate a STL, which we then can input into the AM machine and replicate the part. So on the right-hand side would then be the question, how accurate is this process? And in this case, we come to the accuracy. So we use the CT in the terms of quality management. So when we manufacture that part, then the question is the part good in terms of the shape? We heard about the pores. And in this loop, the CT acts as the quality control of the manufacturing process. So in principle, a little summary and outlook. So well, as I hope I could show you that CT is, I would call it predestinated as a measurement technology for the additive manufacturing, because as in the additive manufacturing, the shape of the part is arbitrary. So we do not have cuts that prevent on a tactile or on an optical to determine the shape with inside structures. This is not a problem of the CT. So the geometries are almost unlimited. In terms of accuracy, so we have an advantage. This CT is already standardized in terms of accuracy. So that means we have guidelines we just follow to determine the accuracy. I showed you the slide with the artifact, with the tactile calibrated artifact. So concerning the material, so the material is a good thing or a bad thing. So we do have the possibility to resolve different kinds of materials by its density, as we can resolve inclusions by higher density or a lack of material as pores when it is a lower density in a volume. But well, this is the good point. The not so good point is that we have a limitation on the density, because think of the LED. LED is good for the shielding, but not as scan objects. So there are limitations when it comes to very high density materials. And the combination as measurement technology and additive manufacturing, this creates new application, this creates fast process change. So well, improvement in practice can be in the design and the manufacture of the artifacts. Especially this comes true when we talk about calibrated artifact for porosity, because this, due to our knowledge, does not exist yet. Well, from the metrology side, I think this is clear. We have no method for a calibration of pores except for the CT. So it would be good to have a reference method. But well, as this is not the case, we need to define process chains in combination with other technologies like mechanical testing. Okay, so thank you very much for your attention, and we're glad for your questions.
Can you hear me? Okay.
Loud and clear.
Okay, loud and clear. Might not be a fair question, but I'll ask it anyway. When can we have like aluminium properties that, you know, are approaching what we do with subtractive aluminium today?
Oh, that isn't a very fair question, but I'll try and answer it. I think the development of AM-specific materials is getting us close to it. I would argue from some of the subtractive materials that I've seen, it depends on your raw alloy and how well that's processed as well. So I don't think anything is flawless. But there's definitely work being done at the moment on AM-specific alloys where we are going to stop, trying to chase a legacy of AMing things that were never designed to do so, which is, I think, one of the biggest hiccups that we've had of trying to get process parameters for cast alloys, essentially. But we're close. I'll let you know.
Thank you.
To run around for the...
Thank you for the presentation. Can you do in situ testing with your solution, or because this would help to define what's the right threshold for sizing this porosity, right? Because everything that doesn't affect then your mechanical properties, you can disregard it.
Ooh.
May I answer?
Yes, you go for it.
So talking about in situ, I think you talk about, your question is in terms of in situ scans.
Yeah, so basically scanning while testing. So I know, for instance, that you can do it in a synchrotron.
Yes.
Yes.
I don't know
Yes.
if you can do it
Yes.
in...
I come from a synchrotron background, so I totally agree with that. I think Uwe, it is worth
Yes.
you answering it.
We will soon prepare this. In fact, we can put different electricity, power, water, whatever you need in the cabinet, and so this we will soon implement at Renishaw.
Thank you.